I'd like to thank Professor Sang-il who organized this very nice and frequent and almost regular seminar. So I'm very honored to give a talk at the last Discrete seminar in this year. Okay, so today's my talk, the title is A Combinatorial Approach to the Power of 2 in the Number of Involutions. I guess some of you are familiar with this title because last year I gave a talk about this in combinatorics conference at KAIST. And of course, this talk is not the same as the previous one. The main difference is, first, I speak in English, and the second, I made some improvements. And at that time, I didn't realize that the main result of mine is already known. So now I found that my result was already known, so I added this, a combinatorial approach to the power of 2 in the number of involutions. So this is a joint work. This is joint work with my advisor, Professor Dong-Soo Kim. Okay, I'll start with some definitions. Here, Sn is the set of permutations of n. Here, bracket n denotes the set of integers from 1 to n. So let A be a finitely generated group, and Hn over A is the number of homomorphisms from A to Sn. And let Ma of D is the number of subgroups of index D in A. And Wolfart proved the generating function for the number of homomorphisms. Here, very simple. It has a very simple formula. And throughout this talk, I assume that P is a prime number. So here, this is the cyclic group of order P. Then let tau P of n be this number. So this is equivalent to say that it is the number of permutations in Sn satisfying this relation. Then if you use this formula, then we have this generating function. So this is the tau P of n is the main interest of this talk, and especially we will consider P equals 2. Okay. So if P equals 2, then this is the number of involutions. Okay. So let odd P of n be the maximum integer k, such that P to the k divides n. So for example, odd 3 of 72 is 2. And Chola, Herstein, and Moore proved that the order 2 of number of involution is at least this number. And a little later, Grady and Newman proved that this is true for every prime number P. Okay? And in fact, Ochi found this exact value of this for all primes less than or equal to 2. Equal to 23. In particular, if P equals 2, then Ochi's result says that the order 2 of this number is this. Here, delta r, 3 is the chronological delta. So it is 1 if r equals 3 and 0 otherwise. So in this talk, we want to prove this combinatorially. They proved this some elementary number theory and p-adic theory. And in this talk, we will only use combinatorial argument to prove this. Okay.
So even for prime P as well?
Yes. Actually, we can prove this. It is more general than this. But first, I'll prove this because for simplicity, and then later I show you that our method can be applied to prove this. Okay. So before starting, let's see some simple theorems about the number of involutions. Here, Tn is the number of involutions. And in the same paper, they prove that if m is odd, then m is a period of the sequence this. So this is the sequence of number of involutions mod m. And that is the number of involutions satisfy this modular equation. The proof is very simple. Because we can easily find this recursive relation for the number of involutions. So because of this recursive relation, it is sufficient to show that Tm and Tm plus 1 are 1 modulo m. Because T0 and T1 are 1. And Tm, you can express Tm as this summation, because the number of the involution is a partition of integers from 1 to n, with each part has 1 or 2 elements. So we can express this, and by simple formulation, we have this. And here, if j equals m, then this is 1, and otherwise, this is less than m. So everything except j equals 1 is divisible by m. So you can see that Tm is 1 modulo m. And using the recursive relation, Tm plus 1 is 1 modulo m. So we prove that this relation. And they didn't mention the next theorem, which is also very easy. The next theorem is m is a period of this sequence, but actually it is the smallest period of the sequence. So it is also very easy. Let D be the smallest period, then D must divide M. So we have this relation, and because D is a period, we have this. Because T2 is 2. But in this recursive relation, we have this. Here we get M divides D. That means D equals M. So we have that. In this sequence, M is the smallest period. But here, we assume that M is odd. So we can ask, what if M is even? But later you will see that if M is even, then this sequence does not have a period, because it has infinitely large power of 2. So, but we will we will consider a partial answer. So we will assume that instead of the number of involutions, we will consider the number of involution, the odd part of the number of involutions. So number of involutions divided by the maximum 2th power. Okay. So now we will prove the that theorem I showed you before. So recall that tau 2n is the number of permutation with this relation. That's exactly the definition of involution. So in here is the set of involutions in this permutation group. And let Tn be the number of involutions, that is tau 2n. And permutation, involution, we can consider involution as an incomplete matching on n vertices. So this is an involution in cycle notation. Then we add an edge if 2 integers are in the 2 cycle. So we can consider this involution as this diagram. So we call this an edge and this a vertex. So each connected component in this graph is a fixed point or edge. So now we will define a map from an involution. So this is an involution, And here, first I make a block for blocks containing the first two elements, and then a block containing the second two elements, and so on. So the last block may contain elements less than 2. So here it contains only one element. Except the last block, every block has two elements, vertices. So we will call this block a normal block. So normal block contains two vertices, and we call this block the special block if it exists. So we map, the map is not yet done. We remove every labels of the vertex. And then if there is an edge which connects two vertex in the same block, then we remove that edge. So we have one such edge, so we remove this edge. So our map is this. So we map, the map send this involution to this diagram, which we will call a block graph. Okay. So because, let Gn be the set of block graphs obtained in this way. And because this is a map, you can partition the set of involutions. So phi inverse of G is the set of involutions which maps to G in this map. So we have this partition, set partition. And because these are disjoint union, Tn, the number of involution, is the sum of this number. So this, we can see how this number act by seeing this number. Okay. And so how can we count this number? So each involution in this set can be constructed by this way. So we label two vertices in this normal block with these two integers, and add an edge between vertices in isolated normal block. Because isolated normal block, okay, let's see. If this this is an isolated normal block, it is isolated block, and because if you remember that we removed an edge if there is an edge here. So from the first step, the involution may have an edge or not. So we can add an edge or not. So the dilemma is the size of this set is given by this number. So here M of G is the number of two block cycles in G. Here two block cycle means two cycle. This is a cycle consisting of two blocks. So here M of G is 1. This is because for each block we can choose two ways, because we can here we can add an edge or not, and here we can label these two in two different ways. So we have we multiply 2 in these times and then divide by this number, because this can be obtained in two ways, but they are considered to be the same. So we have the cardinality of this set. This is the main lemma. Okay. So let Gn, small gn, be the number of block graphs without two block cycles. And then the number of block graphs with exactly I2 block cycles is equal to this. This is because we choose 2I blocks which make 2 cycles, and then this is the way to make them 2 cycles. and this is the way to do the rest. Here, m double factorial denotes the product of all positive odd integers less than at most m. Then we have this formula for number of involutions. Okay. So we change this using the lemma, previous lemma. We have this, and we can change this term to this. Here, by changing with some simple method, we get this. Here, we see that these are all odd integers. So we see that it has at least this power of 2. That is the proof of the first theorem of Scholar et al. Okay? And actually, we can find the exact order 2 of this number. Okay. So that's the theorem. Here, Gn denotes the number of block graphs without 2 block cycles. And we can prove that it has this recursive relation. And we can, using this recursive relation, we can find the first few values of Gn. And let's see here. We want to count the maximum k, which such that 2 to the k divide this number. So here it is fixed. So we want to find the order 2 of this number. And here it is the sum of several numbers. And the first, my claim is the first summand has the smallest order, which means that determines the total order of this number. That is very easy because of this number, this table. So here we can see that the first number has the smallest order 2. And this number, this is 1 only if r equals 3, and otherwise this is 0. So we have this exact order 2 of Tn. This is the combinatorial proof of OCI's result. And in fact, our method can be applied to weighted version. So we can give the weight on an involution. So pi is an involution, or it is an incomplete matching, as I showed you before. So fix of pi is the number of fixed points, and edge of pi is the number of edges in pi. Then we define the weight of pi by this natural way. So x to the fix of pi and y to the edge of pi. And Tn of x comma y is the weighted sum of involutions. And here, if y equals -1, then this is a famous orthogonal polynomial called Hermite polynomial. Dr. Dendrek is an expert on this subject, so if you have any question, then don't ask me, but just contact him. So anyway, the Tn sub x comma y is the weighted sum of involutions. And of course, we can divide the set of involution as we did here. So here we want to define the weight of the block graph satisfying this relation. It means the weight of block graph G is the average weight of involutions in this set. That will help us to find the formula for this. So we want to define satisfying this relation. Okay. Here, so this is the isolated normal block. At first, the involution may be this or this, so except that every edge is preserved. So except this edge, every edge does not disappear. So we wait. So this is x squared and this is y. So we put weight x squared plus y over 2 on each isolated normal block, and every other we put the same weight. So here G prime is the block graph obtained from G by removing the isolated normal blocks. So except this, we put the same thing, and then for this we put weight this. And you can easily see that this is the average weight of this permutation, this weight involutions. And here note that it may look very strange, but if we put x comma y to be 1 comma 1 or 1 comma minus 1, then it is an integer, right? Because this is 1 or 0. Then because this is the average weight, we can calculate this like this. So now we can do the same thing, exactly the same thing. So we have the formula for the weighted sum of involutions. Okay? Here, in particular, if x equals 1 and y equals -1, then we have this formula. So here, with this formula, we can find order 2 of this number. Here, you may notice that this is the weight signed sum of involutions. Let's see. Okay, so to find the exact order 2 of this number, we need to study the behavior of this number, and we can prove that it has these two recursive relations. And using this recursive relation, we can prove some divisibility property. I will not bother to prove this.
How do you find such a reconciliation? Do you just try to prove it, or there's some other automatic tools, or?
It's how can I say? I did similar, like I used the similar method to find the recursive relation of number of involutions, like Tn. Yeah. To prove this recursive relation, the last element can be connected to some of this, or it can be a fixed point. So that's the proof of this generative function. And I used similar method, but a little complicated than this. So using this, I proved this. Actually, I wanted to find the exact order 2 of this number, but I failed to do that. And actually, I don't need to find it, so I didn't wanted to find the exact order 2 of this. I only need to know the value of this mod 4. So this means it contains at least 2 truths. Anyway, using these recursive relations, we can find this number for the several few values of this, and use the same method. We can prove that the order 2 of this signed sum is this. And these two, using this table, we can consider odd involutions and even involutions. So a permutation is even if the sign of that permutation is 1, and it is odd if the sign is -1. This is the definition of definition. And as I mentioned, this is the signed sum of involutions, because in the involution, every 2 cycle contributes -1 to the permutation, and fixed point contributes 1 to the permutation. So this is the signed sum of involution. And let Tn even be the number of even involutions, and this is the number of odd involutions. Then Tn even is the sum of this divided by 2, and T odd is this. So we can immediately get these two, because this dominates this. So if we add these two numbers, then the order 2 will be k plus 1. And because we divided it by 2, we have k. So the problem is this. Using some elementary number theory, I was able to find these two entries, but I couldn't do this for this. And in fact, I conjecture that there is no such integer here, but there is a p-adic integer instead of an integer. So I think it must be a p-adic integer. P-adic integer is
Order 2 of something is number.
Yes. P-adic integer. Okay. P-adic integer is a sequence of integer. Something like this. 2. Two-adic integer is a sequence of integers such that the first how can I say? The first subsequence are equivalent mode. So these are equivalent to mode 2. Okay, mode 4, and these are equivalent to mode 8. I think it's not correct. Anyway, I don't want to. I forgot the definition, but it's not difficult, and you can find any. You can Google this. Okay. Anyway, so my guess is. It doesn't seem like an integer. Okay, here it means it is 1 if k is an odd integer and 0 otherwise. Okay, so now I want to extend my method to prove the general case. So here p is a general prime number. I wrote p is greater than or equal to 3, but it can be applied to p equals 2 case. So if permutation satisfies this relation, then it consists of fixed points and p cycles. So here tau p of n is the number of permutations with this relation, and let Sn comma p, Snp be the number of set of permutation with this relation. SNP is the initial of KAIST president. So here, so we can identify permutation with this diagram, and the gradient Newman's theorem is this. We can prove this. Okay. So first, similarly, we can define the map. Here, we make a block consisting of the first p integers, and then make a next block consisting of the second p integers, and so on. So the last block may consists of integers less than p. So if it consists of integers less than p, then we call it the special block, and others are called normal blocks. So here, if p cycles are in a single block, then we remove every edges. Here, edges are directed. So we remove this p cycle. First, remove every label and remove p cycle, which is contained in a single block. So this is the map phi of p. So G and comma P is a set of directed block graphs. So I didn't mention, but this is directed block graph. Then this number can be computed by this. So it is enough to show that the order P of this desired number. So here, let's let I and B of G be the number of isolated normal blocks. So here we have two isolated normal blocks, and we see connected components are single fixed points or p cycles. So two connected components C and C prime not contained in an isolated normal block. So these two are not in our interest. So two connected components are called identical if they have the same sequence of visiting blocks. So here, these three gray paths are identical, and these two purple cycles are identical, and these two black fixed points are identical. And if one of these cycles is ordered reversely, then they are not identical. They are identical because they have the same orientation. So divide all connected components up to identical classes. So we define the type of G to be this integer partition, which means weakly decreasing sequence of integers, where each integer denotes the number of components in an identical classes. So in this example, I and B of G is 2, and type of G is 3, 2, 2, and 1, 1, 1, and 1. Okay? So the type of this graph is this. Then, now we can find this number. If the type of G is this, then the cardinality of this set is given by this number. Can you see why this is true? So, assume that we have this block graph. How many ways to construct permutation which is corresponded to this? So here we can label these 3 with 1, 2, 3. So there are 3 factorial ways to label this without considering the later thing. So 3 factorial ways, and so on. And what about this? There are, if it was a p cycle, then there are p minus 1 factorial ways to construct a p cycle. And if it was if there was no p cycle, then there is one way to label this, because all the same. Okay, so there are this many ways to construct from isolated normal blocks, and this many ways to construct from this, and this is for special blocks. And we have to divide by this number because we have the same thing if they are identical. So we divide by this number. And here we can now easily, we have done almost. Each Ci is less than or equal to P, because there are at most P identical component. Because, yeah, it's easy. And the equality holds, I mean the equality here holds, there are P cycles in P blocks. Okay? So if Ci equals P, then it needs P squared vertices. So here there are at most, okay, here what is the maximum number of P factorials here? That is this. Because each P factorial needs P squared vertices. So there are at most this number of P factorials here. And here, this is divisible by P, by Wilson's theorem. And this is, of course, divisible by P. So we have at least P to this factor. And the denominator is at least this. So we have this relation. This lower bound. So because this is the sum of these, so we have this. So this is a combinatorial proof of Grady and Newman's. And in fact, at the beginning of the talk, I mentioned that M is the smallest period of this sequence, and let beta n be the odd factor of the number of involutions. Then, using the formula I showed you, you can prove that using some many elementary number theoretic calculation, we can prove that 2 to the s plus 1 is the smallest period of this sequence. So this is a partial answer of even case.
When you define beta n, you might want to divide it by 2 to the order?
Oh, you're right. I am sorry. I have to write. I should write it here. 2 to the something. So that is the order or odd factor of the number of involutions. So beta n is always odd. Yeah, so I was able to prove this. So this is the end of my talk. Thank you very much.